In this tutorial, I will solve some problems related to 2 or 3 degrees of freedom system to review some fundamental topics related to vibration of n degrees of freedom system. We will start with the vibration of a simple card and a pendulum. Then we will move on to compare the natural frequencies of a 2 degrees of freedom with a simple single degrees of freedom system. We will move on and we will discuss the Lagrange approach when we solve a simple problem like this 2 degrees of freedom system, and then we will repeat the same problem using Newton approach, meaning drawing the free body diagrams and finding the differential equations. This is an interesting problem. We will solve it using 2 different coordinates. First, we will use both for the bigger cards and the smaller card absolute coordinates. Then we will solve the same problems. This time we will use a local coordinate for the smaller card inside, and we will compare the result. After that, in this problem, we will find out the natural frequencies that result in zero motion of the smaller mass, which is subjected to an external harmonic load. In other words, the 2 other masses act as vibration absorber for this system. And lastly, we will see how we can decouple a 2 degrees of freedom system when it is subjected to an external load, how we can solve and deal with that problem. All right, so let's get started. There are many problems and interesting problems. I'm going to turn off my camera, so we'll focus only on the solution because you don't need to perhaps see me. Let me adjust my tablet here. All right, let's start with the first problem. In this problem, typically we use Lagrange approach because it makes the solution easier. I need to find T, the kinetic energy. Well, I have the card, which is half of m x dot squared. For the pendulum, since the pendulum only is a concentrated mass m there, all I need to do is finding its absolute velocity. Obviously, this pendulum, its velocity, if I want to be accurate, it's going to be in that direction, perpendicular to the link of that pendulum. However, since its vibration theta is small, I can assume that the velocity is almost horizontal, and this value is L theta dot. Therefore, the kinetic energy of the pendulum is half of m, its velocity, and since it is inside a card, it also moves with the card. My velocity this time is sum of x dot and L theta dot. That's my kinetic energy. The potential energy for this system is half of k x squared for the spring, and obviously I have the mass moving up, which is mgl 1 minus cosine theta. Again, since we are in vibration, theta is small, I can replace that by the 1 minus theta squared divided by 2. That's the Taylor expansion. Therefore, my u becomes half of k x squared plus mgl theta squared divided by 2. If I find my t and u successfully, the rest are just some tedious math. I need to use Lagrange equation. The Lagrange equation says derivative of d with respect to time, derivative of t, partial derivative of t with q dot plus derivative of u with q equal to any external load here, q. Well, if that's the general Lagrange, if q is equal to x, my first variable, it means now I have partial derivative of t with respect to x dot and derivative of u with respect to x equal to, I have an external load f sine omega t interaction of x. Let's do the derivative once. d dt. So first I try to do the derivative inside bracket. Derivative of t with respect to x dot is going to be give me mx dot plus mx dot L theta dot, and derivative of x dot will be just 1. And u with respect to x, and here I just have sine omega t. Now I can do the derivative inside the bracket with respect to time, and I'm going to get mx dot and ml theta double dot plus kx equal to f sine omega t. So that's my first actually equation. Now I repeat the same, this time q equal to theta. My equations will be derivative of t, partial derivative of t with theta dot, and derivative of u with theta. I don't have any load, so it's equal to 0. Derivative with time, and the derivative of t with theta dot will be mx dot L theta dot, right? And then I have the inside bracket, which we need to be careful, is ml. It's L. Then derivative of u with theta, which will give me mgl, simply theta equal to 0. And here I can simplify it, doing the derivative one more time with time, mx double dot, multiply by L. Then I have ml squared theta double dot mgl theta equal to 0. I should be able to cancel this L, simplify it. And here is my second equation. Now, typically with 2 degrees of freedom, we are asked to actually rewrite the equations in a matrix format, which that part should be very easy. We can do that one as well, which it gives me a 2 by 2 matrix, which 2m here, I have ml, and I have m, and then I have ml as well here, right? So here I have an x double dot, and then I have the theta double dot. And if I do that correctly, I would end up for my stiffness matrix with a k here, 0, and nothing there. And then I have mg over there, x and theta equal to f sine omega t. Something to pay attention, since we have a diagonal matrix for k, it is, we'll see that matrix is decoupled. However, the system is coupled dynamically. We have non-zero off-diagonal parameters there. All right. Let's move on to the second problems. Here we wish to compare a single degrees of freedom system, which we learned before, and we know its equation simply is mx double dot plus kx equal to 0. Obviously, this one gives me the natural frequency of k over m. But for this 2 degrees of freedom system, if we write the equation, we are going to end up with matrix equations. Now, I have x double dot 1 and x double dot 2 here. And for k, I'm going to have 2k minus k, and 2k there. And x1, x2 equal to 0. So as you see, And instead of just one value for mass and one value for K, I ended up with a matrix of value for mass and a matrix of values for stiffness, which obviously, because it's a 2 degrees of freedom system, we'll learn how to find the natural frequency of this system, simply determinant of K minus omega squared m equal to 0. If I solve the algebra, which I did, and I'm going to skip the algebra here, I'm going to find two answers. One is K over M, and another one is 1.5 K over M. So which we a smaller one, we call it natural frequency of 1 and natural frequency of 2. And similarly, we learned that, let me just move this a little bit up there, that if we solve this algebra, linear algebra problem with vector u and v, it gives us the ratio of the amplitude, which will be 1 for that frequency, and it will be -1 for the other one, which we call them mode shapes, and we learned about them before. Now I want to focus on that particular mode shapes, all right? If the ratio of u over v over there is 1, it means that this system with these two masses are going to have the same amplitude in that particular natural frequency. What does it mean? Simply, it means if the first mass moves by 1 unit, this mass as well moves with 1 unit. And it means there will be no deflection in that spring, right? Because the both sides, they move by the same amount. Well, simply it means then the middle mass has nothing. It does nothing, right? It applies no force. In other words, I can pretend that it does not exist. Or I can think about actually that system, let me just correct this one, is being two independent single degrees of freedom system, which each of them has its own coordinate, right? And simply their natural frequency of each is K over M. So that's the comparison. In other words, if I want to compare the first mode of the system on the left, it's like to pretend that it composed of two single degrees of freedom system, and each has the natural frequency of K over M, which, as you can see, is exactly equal to our first natural frequency, and physically it makes sense. All right, moving on. Now I have a system which I wish to solve it by solving, meaning finding the differential equations of motion with two methods. It's mainly a review of Lagrange and Newton approach. Let's first do the Lagrange approach. T is very simple. I have half of m x dot 1 squared plus half of m x dot 2 squared. And potential energy, since there is at equilibrium pre-stretching springs, we don't worry about the weight gravitational potential energy. It's only the springs. So I have my first spring 2K, which deflect by x1. That's easy. Then I have the other spring. By other spring, I mean the one on the right. So that one is also half of K x2 squared, right? And because this spring is attached to that mass, and that mass is moving by x2. Of course, in reality, we can pretend that there are some perhaps rollers on the side like that, meaning that that mass is just moved vertically. We need to just be careful about the spring here, which it moves by x1 from that side, and it moves by x2 from that side. So it's then potential energies half of the stiffness, the difference between these two, x2 minus x1 squared. If I got the T and U correct, the rest is again algebra. I need to do the Lagrange derivative with respect to 1. And I'll do the same with respect to second one. I don't have any external load and I don't have any damping. So the Lagrange equation becomes very simple. I'm going to skip actually the algebra here and just write for you the final result. But please do it on your own. Do the derivative on your own and compare with my result. You never know. I might have done a mistake, which you can tell me. Or my answers match yours, which we will both be happy. All right, so that's the answer I got. Hopefully you got the same answer as mine. 0. All right. Now we want to repeat the same problem using this time Newton approach. For Newton approach, we will need to draw our free body diagrams. So I have mass 1. I'll just put it there. And I have second mass. I put it there. So I know what's going on there. All right. So that part is easy for this spring. I have the force 2K stretched by x1. And that one also is easy. I have the actually K multiplied by x2. Because that spring from one side is attached to the ceiling and another attached to mass M, which move by x2. Well, the spring in the middle, if I write it as x2 minus x1, it means we pretend it is under stretch, meaning that it moved by x2 down here and it moved by x1 here, and we pretend x2 is larger than x1, meaning it is under a stretch, right? And then we have the reaction on the other one, which is actually the same force now. So I have my free body diagrams successfully there. The rest is just a story of writing the Newton law for the x double dot one. Need to be careful about the direction of the coordinate that we choose. Here is x1 and here is x2. Therefore, I have minus 2 x1, and then I have plus 2k x2 minus x1 equal to mx double dot 1. And I repeat that for the second one. For the second mass, I have the load kx2 and I have the load 2k x2 minus x1 equal to mx double dot 2. All right. Now, we'll simplify the equations and we write them in matrix format. Hopefully, we get the same answer as before. This is what I got. Hopefully, you get the same as mine, 4K. If not, you can again let me know Perhaps I missed something, or maybe I did some mistake, which it may happen, of course, when we just solve it fast. All right. Well, if you are interested in finding the natural frequency of this system, you know what to do. Well, simply, we know this is our mass M matrix, and this is K, the natural frequency. We just need to set the determinant of K minus omega squared M equal to 0. Or for simplicity, maybe we call this one lambda, and lambda means omega. I'm just going to leave the algebra with you. I tried, and this is the answer I got for lambda. I got lambda equal to 7 plus minus 17 divided by 2 km. But please solve it on your own. Make sure you get the same answer. You may simplify it a little bit. And remember, these are lambda. In order to find natural frequencies, you need to just find the square. And here we have plus and minus. Obviously, the minus one gives you the smaller value, which is your omega 1, and the other one omega 2. Well, moving on to this card problem. As I said earlier, we plan to solve it with two approaches. First, we want to use absolute coordinate, meaning that I'm going to choose the coordinate x1 for the card, measuring it from the wall, and I'm going to use coordinate x2 for the other mass, all right, for the other mass, measuring from its center using x2, right? So both of them are absolute coordinates, meaning that we measure them from a wall which is fixed to the ground, all right? Let's just do that one. And I will find out the value of T, energy, half of, just be careful, the mass of the card is 2m, half of 2m, and it moves with the velocity of x dot. Easy. And the other one, its mass is m, and it moves with the absolute value of x dot 2. So we don't need to be worried about anything. And then I need U. So I have 3 springs. So something that I will do, since these 2 springs are actually parallel, what I'm going to do to make my life easier, I'm going to pretend that the spring is not there. And instead, I have the 2K there, all right? Because those 2 springs, they were parallel, and I'm allowed to do that one. Makes a little bit maybe writing easier. So the first spring, K, it just moved by x1, or stretched by x1, half of K, x1 squared. Here is the second spring. Second spring, if we pay attention carefully to the previous problems that we solved, it moves by x1 from one side and compressed by x2 from the other side. Keep in mind, it is inside the card. However, this is how we measure it. So if you are standing outside and you're watching this spring 2K, you measure that how much it moves from the right side and how much it moves from the left side. So you're going to conclude that this spring, it actually moved by x2 minus x1 squared. So we have T and U, the Lagrange approach. You know the formula for the Lagrange approach, derivative of T. As we solved in previous problem, Q dot U with respect to Q equal to 0. You set your Q equal to x1, and then you repeat that, set your Q equal to x2. And I'm going to skip the algebra here because in previous problem, you saw how it works. I'm just going to write the final answer for you in matrix format. So again, you can compare and hopefully you get the same answer as mine. X double dot 1, X double dot 2. But if you didn't get the same answer as mine, it doesn't mean you can double check it, of course. And after you are 100% sure that you are correct, then I might have done a mistake somewhere along the way in algebra, but the T and U, they are correct. By mistake, I mean not fundamental mistake, it's mainly the algebra mistake. So here we are. We got our differential equations in matrix format. From here, we know how to find the natural frequencies and the mode shapes. If I do the math, and I'm just going to write the result here, I'm going to get my first natural frequency, which is 2.52 K over M. Sorry, that's my second natural frequency. My first natural frequency is going to be 0.79. And my second natural frequency will be 2.52. Perhaps I've done some rounding and simplification. And for the mode shapes, by mode shapes, I mean the actually x1, x2, the ratio. For the first mode, I'm going to get, or I got actually 1.15. Again, I'm going to just try to make sure that I got the right number. Yeah, I got 115 and x1 and x2. For the second mode, I got minus 0.2. All right, that's the mode shapes. But again, I've done some rounding and make sure that you check the math and see how it works. However, from the fundamental, when we calculate T and U, you saw how it works. And this is the formula we use. I'm going to now repeat the same problem, but this time I'm going to use different coordinate. And then we can compare, of course. The first coordinate for the card, obviously, I use a coordinate and I measure it with the wall. But this time, my second coordinate, this is where it gets interesting. It's going to be a local coordinate. So my x2 actually is measuring the motion with respect to the card, which actually it makes more sense because if we put some sensors for this card, imagine this card is part of a machine and we wish to do some measurement. Obviously, we measure the wall and the distance of a card with respect to the wall, but we measure the motion of the mass inside the card with respect to the card, because then we can do some algebra and find the absolute value. But in terms of solving the problem, let's see how it affects our solution. All right. Similar to what we did before, let's just get rid of that spring. And we pretend that this other spring is 2K, right? We can do that because these two springs, they were parallel. It's again just to make the math a little bit perhaps easier. All right, let's see how things change here. T, my kinetic energy for the card is the same, half of m, 2m. Card has the mass 2m, x dot 1 squared. Here it's where it gets tricky for the mass inside the card. Mass is m, but we need to be careful. Its absolute velocity is x dot 1 plus x dot 2 squared. Remember, you add the velocity linearly, because if you're standing outside and you're watching mass m, obviously its velocity is x dot 1 plus x dot 2. What about the springs? The spring outside is k, and it's moved by x1. But the one inside, obviously, now that you measure the deflection with respect to the wall, so it means this spring is being deflected. Sorry, it's again 2k. It's being deflected by x2. All right, you need to be careful, because if you look at the spring, the 2k spring inside the cart, it doesn't matter how much x1 is moving. X1 maybe moves few meters, right? But the stretch of the spring inside the cart is going to be x2, all right? It's a little bit different than, I'm going to go back, and this one. Here, since your measurements were with respect to the wall, it means that you are watching the two ends of the springs, the right end and the left end, and you see the right end moving by x2 and the left end is moving by x1. So that's why you got different terms here compared with that one. So we have T and U. Obviously, we use our Lagrange equation. I'm going to skip that part and see what we get. Here, the equations we got here, 3m, m, and m, x double dot 1, x double dot 2, plus k 0, 0, and 2k, x1, x2 equal to 0. Now let's compare. Obviously, you see the difference here. It is diagonal for the stiffness matrix, and it's a coupled matrix for the dynamic one, unlike this one, which you have different values, right? If you compare them. Let's just pretend that we don't know about the previous one and we just wish to find the natural frequency. We know how to do that one. We'll use the determinant of matrix K minus omega squared m equal to 0. We'll do the math, and here our result. So first natural frequency is 79 km, and the second natural frequency is 2.52 km. Well, that's interesting. Despite our coordinates, our natural frequencies are exactly the same as before. And this is actually what we expect and what we learn. No matter what sort of coordinate system you use, the system still has the same natural frequencies, because natural frequency depends on stiffness and mass and the way they attach to each other. It's independent of the coordinate you use. But let's find the actually the ratio of x1, x2 and see how that is going to change. So x1, x2, x1, x2. I'm going to just write the result for you, and hopefully I did it correctly. So this is what I got. For x1, x2, I got actually a negative number here, is 7.1, and x1, x2, I got that. So here is my mode shapes for this coordinate. Well, here obviously we got different answer compared with the previous one. All right, let's just go back and look at the numbers we got there. And that's obvious because our definition of x2 is different, right? In the previous problem, x2 is measured from the wall. Here, x2 is measuring from the cart, actually, and that's why we expect different answer. So in conclusion, when you change your coordinate, you get the same natural frequencies, but your mode shapes would be different. However, if you can do some perhaps manipulation between this result and previous one, because you know in the new one, x2 actually is x. If you compare that one, like for this system, x1 plus x2 will give you the same x2 that you call it there. Perhaps it would be better if instead of calling this one x2, we'll just use a different parameters. Maybe we'll call it x3 or something else. However, you got the idea. Let's move on to this problem, which is very interesting. It's a concept of vibration absorber. I have a 3 degrees of freedom system. It's a good practice for you to solve this 3 degrees of freedom system by Lagrange approach and also by free body diagrams. I'm going to do the free body diagrams for you so you can compare your result. You can pause the video and perhaps draw the free body diagrams and compare with mine and see how far you could get it right. So I have a load there from data spring, and then I have the springs here, the reaction, and then I have the spring there and the reaction. So we don't worry about the weight. So that one is kx3. The springs over here, kx2 minus x3. And the one here is going to be x1 minus x3. Right? And of course, I have the external load there as it is, F sine omega t. The mass here is 2m, and each of them are m. Writing the formula, sum of the F is equal to ma for each of them, and being careful that the mass here is 2m. I'm just going to write the final result for you, and please repeat the same problem using Lagrange and compare your result. So here is what I got. I got a nice diagonal mass matrix. X1, X2, and X3. And then I got my stiffness matrix, K, 0, minus K, 0, K, minus K, minus K, minus K, 3K. And here I have X1, X2, X3. And here I have F, nothing, and then nothing there, sine omega t. So as we expected, our matrix are 3 by 3 because we have a 3 degrees of freedom system, all right? Now I can find, perhaps I need a little bit of more room. Perhaps my approximation for, I'm gonna just make it a little bit smaller. All right, that's good enough. I need to find the amplitude of x1. This is what we are interested. We are interested to find the frequencies that make x1 0. So what I will do if I choose x1 t, x1 sine omega t, so I guess that would be the answer. X2 would be x2 sine omega t, and x3 will be x3 sine omega t. All right, which is obvious because I have here sine omega t, right? So most likely this function would be a good fit for that one. I substitute all of that and simplify it. I'm just going to write the result. After we do the simplification, we are going to get k minus m omega squared. And here 0, obviously. Then we have minus k. Then we have 0, k minus m omega squared minus k. And then we have minus k, and 3k minus 2m omega squared, x1, x2, and x3 equal to f0 and 0, right? If you substitute that one, and please do so, of course, this sine omega t, you can get rid of that because you have it on both sides, and you're done. Now you have a simple algebra equation, which you know how to solve that one. x1 will be, we use the Kramer's approach, which on denominator we have k m omega squared, 0 minus k, 0, k minus m omega squared minus k, minus k, minus k, and 3k minus 2m omega squared. Oh. And then for the numerator, we just substitute the first column with the right-hand side, f0, 0, and then we repeat the same. So I have 0 minus k, k minus m omega squared, minus k, and here 3k minus 2m omega squared. All right, so that's the response of actually x1. Now, this response, of course, can be a little bit simplified. Again, let me just make everything tinier so I have more room. Or perhaps what I can do, let me just move that problem to the next slide. Maybe that's a better idea. All right. So this x1, I can rewrite it one more time. I'm just going to call the entire things here delta because it has too much things to write and I don't wish to write it there. I need to do the multiplication here. I'm glad that we have 0 there, 0 there. So all I need to do from that column and that row, I just have f, and I multiply that f by determinant of that 2 by 2 matrix. If you forgot the matrix multiplication, please go back and check some of your past notes, or maybe on YouTube you can find like a nice video that explains to you how to do a multiplication for a 3 by 3 matrix. 2 by 2 is easy, 3 by 3, right? Which is very actually straightforward. You just have this f multiplied by that 2 by 2 matrix, and the rest are 0, so we don't worry about them. If they were not 0, we repeat the same process. All right, so I can simplify it one more step. Now you realize why I call it f, delta. So I have f, and 2 by 2 matrix is easy. K minus m omega squared multiplied by 3k 2m omega squared minus k squared. So here is the response of x1. Now the question asks, at what frequency x1 becomes 0? Let's x1 set x1 equal to 0. It means k minus m omega squared, 3k minus 2m omega squared minus k squared equal to 0. Do the math, and happily, you're going to find out two values for omega. One is 2k divided by m. Another one is actually k divided by 2m. So what does it mean? It means that these two particular frequencies, x1 is 0. And it means that at these two particular frequencies, which they have nothing to do with the natural frequency of this system. Remember, if you want to find out the natural frequency of this system, to find out the natural frequency of this system, frequencies of this system, you just need to set delta equal to 0, right? The one in denominator. So at these two frequencies, x1 is 0. It means the vibration absorber happened here. But at delta equal to 0, you'll find your natural frequency, and x1 becomes infinity, which we know at natural frequency, the system experiences resonance and infinite response. All right. Moving on to the last question. We have a system and we want to decouple it so we can solve it. It's more like a general problem. I can draw the free body diagrams for this system quickly. We don't need to be worried about the weight, because the weight or the mass has been canceled out by the actually pre-stretch of the springs at equilibrium. So I have my external load there. And then for the loads that I have there, maybe perhaps let's just have some fun. I have the force here, and obviously I have the force there. So that's my free body diagrams. So the force here is k x2 minus x1, and the one here is k x1. So the mass here is 4m, and the mass here is m. And I have my external load there. So since my coordinate are in that direction, I just write the actually Newton law for x double dot 1. I write the Newton law here, which my mass is 4m x double dot 2. Assuming that we do it correctly and we simplify our equations, we are going to end up, I'm just going to write down the result for you, will be m 0, 0, and 4m x double dot 1, x double dot 2. And here I have 2k, minus k, and k, x1 and x2. equal to, I have my loads here, which is 0, and then here I have ft. Remember, question asks us for a general problem, so ft can be any force. All right, I need to decouple these problems because to solve the differential equations, we'll see these elements are there and makes the equations being coupled together, so we're not able to solve them. To do that, we need to repeat some actually steps, which is common for all the problems. Step number 1, you'll find your natural frequencies. That's the easy part. So far, we've done a lot, and we know how to do that one. If this is my mass matrix and this is the stiffness matrix, so simply determinant of K minus lambda M equal to 0. And here you'll find your lambda 1 and your lambda 2. And if you've done this problem and you notice your results are different and you're sure that your result is correct, I might have done math like algebra mistakes. So don't worry, just let me know. But the steps are correct. Step number 2, you find your mode shapes, which you know how to do that one. You just set the matrix that you have there, multiply it by a vector uv, set it equal to 0. You substitute lambda equal to lambda 1, your first actually natural frequency. So obviously remember that here our natural frequency is the square root of that value, right? That's how we define lambda. So if you substitute your lambda equal to lambda 1, you are going to get uv equal to 0.53. And if you substitute your lambda with lambda 2, you are getting uv equal to -8, right? And we write these in a vector format. So uv equal to 0.53. I can write the first mode, choose v to be 1, and this is 5.3. Remember, that's the one way to show it. These two are the same, but typically we'll show it in a vector format like that. And uv equal to -8. Again, I choose v equal to 1. It means it is -8 there. We call this one vector 1. I'll show it with uppercase V, and this one V2. And we say this is our mode 1, and this is our mode 2. Next, I need to normalize these values. There are different ways to normalize them. The one method that we choose to normalize it is so I call it step number 3. We'll find the scaling factor to normalize these two vectors. That scaling factor is simply the square root of V1 transpose matrix M V1. So if you do the math correctly, you are going to end up with 2.1 square root of M. And if you repeat that one for second vector, you ended up with a different value. Hopefully I've done it correctly. So remember, your mass matrix is, I'm just going to write it for you, but please do it on your own. So the first vector transpose is 1. Our mass matrix is M0, 4M, and V is, but keep in mind, then all of that is in power of that, right? So you may choose to treat this one as a matrix, or since you have a vector here, you may consider that a vector multiplied by that. Consider that a vector multiplied by that. If you're doing a factor, like if you're factoring m, which I don't suggest, just be careful about the algebra. So either way, these are scaling factors. Now that I have the scaling factors, the normalized mode V1 is like 53 divided by that number. And V2 is actually -8 divided by 825 and 1 825 square root of m. The solution is easy, just the algebra is tedious. Here in step number 4, we form our modal matrix U, which consists of these two vectors, V1 and V2. It means this matrix is 5, 3, 8, 2, 5, M. Right? I can factor that value. All right, you can do that one, but just be careful since these are two vectors, right? Remember, these are vectors. I have to factor that from each. So I ended up with like that value. This is just to make it a little bit perhaps easier. So it means now I can actually replace that value by simply 1 over m. So that's my modal matrix. That's the one that is going to do the magic. And we learn during the course that if I use this matrix and I transfer my equation, meaning I go from vectors u to vector y, right? So u is the modal matrix. Then I'm going to end up with the equations which looking like this one. An identity matrix, y double dot 1, y double dot 2, and here lambda 1, lambda 2, 0, 0. And remember, lambda is omega 1 squared, and lambda 2 is our second natural frequency squared. Y1, Y2, and on here I have the transpose of U. Remember the transpose. This is how the equations, when we showed in the class, they develop. And my force, which is 0 and Ft. So the good things about now these equations is they are diagonal. It means I have two independent equations, right? And I have the U transpose there, which need to multiply by this value. If I do that part, so I'm going to end up with Let's just quickly do that one. Y double dot 1 plus, I'm just going to replace lambda 1 and lambda 2. We have them over there. Or we just keep them as lambda 1. So it's easier because they are not really nice numbers. 1 equal to ft y2 is equal to 1 over 825 m ft. So what you notice here now, if we have two independent equations, they are simply, they are simple differential equations. They are independent, so I should be able to find yt, y1t, if I know the initial conditions and if I know ft. And similarly, if a problem gives me the actually ft, I repeat that, and I will find y2t. So these are the principal coordinate. Now we need to return back as our last step to our original coordinate, which x is equal to u multiplied by y. Right? So it means my x1t, x2t is equal to u matrix, the modal matrix u, y1t and y2t. Right? And since we have already u, then we should be able to find the value of x1 and x2. All right. Thank you very much for listening. Hopefully it was useful. I know it was long, but I'm just going to turn on my camera. Of course, you see my ceiling now. And it's getting dark. All right. So to summarize, we review several problems together, and you saw in each of them, we deal with a different sort of problems. I'm going to stop sharing the screen. I suggest pausing the videos and try to solve them on your own, and then compare your result with mine. And again, if you notice any mistake, let me know. Good luck. Have a great day.